Good evening, everybody. I am Vibhu Swain from Power Tech Consultant. Today we'll start our webinar number 29. Let me share my screen with you. So in webinar number 29, we'll study about the chapter 5, that is material and energy balance, of book 1, that is general aspects of energy management and energy audit. We have already studied about material balance or mass balance, which is basically based on conservation of material. Material cannot be created or not destroyed. So, or material going into system is equal to material coming out of the systems. And we have already studied the basic principle of mass balance or material balance. We'll try to solve few numericals, particularly on material balance. We have in earlier class we have studied 3 numericals, and we'll continue remaining numericals in this class. This is very important because in the exam you will get a lot of numericals on material balance, energy balance, which has to be calculated to secure good marks. Now, as you all know, material balance is very important because it helps in increase in the product yield. That means it minimize the waste and increase the productivity or yield of the particular any product. Now let us come to a continuous centrifuge milk processing. It says that 35,000 kg of whole milk means it contains fat, everything. Now, it contains 4% fat to be separated in 6-hour period into skim milk. Skim milk is normally does not have much fat. Fat has reduced from 4% to 0.545%. And cream with 45% fat. Cream has also high fat, it is 45%. Now it has been asked, what is the flow rate of the two output streams from continuous centrifuge which accomplishes the separation? So this is basically a separation process in which the whole milk is separated into skim milk and cream. Now, whether this is continuous process, yes, we can assume it is a continuous process. So what we can assume in case of mass balance, the rate of input is equal to rate of output. Now remember this one. In continuous process, time also enter into considerations. The balance are related to unit time rate. Thus, in considering continuous centrifuge separating whole milk into skim milk and cream, if the material hold up in the centrifuge is constant, both in mass and composition, then the quantities of component entering and leaving in the different stream in unit time are constant. A mass balance can be written on this basis. Such an analysis assumes that the process is in steady state, its flow and quantity is held up in vessels that do not change with time. That means in the vessels, milk is coming. Again, some milk is accumulated in the vessels, and the processed milk comes out of the vessels. Now, here mass balance is particularly in the vessels. We are assuming that it is constant. That means it does not, the composition, the mass does not change with time. So, in the continuous process, we can safely assume the rate of mass flow is equal to the rate of mass output flow. So, with this assumption, we solve these problems. What is the mass incoming flow rate? Whole milk flow rate is 35,000 by 6 hours. So, it becomes 4833 kg per hour. Let us assume skim milk is Y and cream is Z. So total mass of skim milk is Y, mass of cream is Z. Now material balance, now what you have to do? You have to write material balance equations. This is the first basis. Now mass in is equal to mass out. So what is the mass in? 5833. Mass out is y plus z. This is equation 1. Then what is the component here? Fat. So fat in is equal to fat out. Now what is the fat in? 0.04 into 5833. That is in the mass. Fat in the whole milk. What is the fat out? 0.45% into y plus 45% into z. Since it is in percentage, so by 100, by 100 and by 100. So this is another equation. So two unknown, two equation y and z can be easily found out. So we can easily solve any problem, maybe continuous process, and we can find out the masses, assuming that the unit rate of mass flow are same by doing some basis and by writing the material balance equations. Now let us solve some example of concentrations. Now a solution of common salt in water is prepared by adding 20 kg of salt to 100 kg of water. So water is 100 kg, salt is 20 kg. To make a liquid density of 1323 kg per meter cube. So liquid density becomes 1323 kg per meter cube. We have to calculate weight fraction, weight by volume fraction, mole fraction, and molar concentrations. Now let us assume the basis of kg. Now what is the weight fraction? 20, and the solution is 100 kg plus 20 kg. So 20 by 100 plus 20, that is 0.167. This is the weight fraction in per unit basis. So in percentage basis, it becomes 16.7%. Now weight by volume. Weight by volume means what is the density? 1323 kg. That means 1 meter cube of solution weighs 1323 kg. So this is the solution density. So 1 meter cube of solution will weigh 1323 kg. But 1323 kg of salt solution will contain how much of salt in meter cube? It will be 1323 kg of salt solution will contain 20 kg of salt into 1323 kg by meter cube divided by 100 plus 20 kg. That means 220.5 kg per salt per meter cube. From these, so 220.5 kg of salt is there in 1 meter cube of solution. So from that, we can find out weight becomes weight by volume fraction will be 2220.5 by 1000. It becomes 0.2205. 1000 basically for the kg. So weight by volume becomes 22.1%. It is in per unit basis. That means from the solutions, we can also find out if density is known, we can find out weight by volume. Now, molecular mass of sodium chloride, salt is basically sodium chloride, is 58.5 gram. You have to remember these equations because atomic mass of sodium is 23 gram, atomic mass of chloride is 35.5 gram. Now, what is the moles of water? How much kg is there? Let us basis is 1000 kg. So moles of water will be 1000. H is 1, H2O, O is 16, so H2O become 18. So moles of water is 5.56. What is the moles of salt? 20 by 58.5 gram, that becomes 0.34. So mole fraction of salt, we have studied in the theory that mole fraction of salt is, or mole fraction of any component is mole fraction of that component divided by mole fraction of all the components. So it becomes 0.34 divided by 5.56 plus 0.34, it becomes 0.058. Now what is the molar concentrations? How much of kg salt is there? 220.5 kg salt is there. in meter cube, and mole fraction you found out already 0.058, that means 58.5%. So and moles of salt is 58.5 gram. So molar concentration becomes 220 by the molecular weight, that is 58.5, that means 3.77 moles in meter. So we can easily find out weight fraction, that is W by W, weight by volume, mole fractions, and molar concentration. This is based on the theories. Now you can note here that mole fraction can be approximated by moles of salt by moles of water as the number of moles of water denominator. Mole fraction is close to 0.34 by 5.56 is become 0.061, and the solution becomes dilute, means this approximation improves. Generally, for dilute solution, mole fraction of solute is close approximation of mole of solute per mole of solvent. So this is basically an approximation in case dilution increases, but in theory, these are the formula and we have to do accordingly. Here we have to just remember the molecular mass of sodium chloride, molecular mass of H2O, and molecular mass of sodium chloride. Now, the second problem is in textile mill, an evaporator concentrates liquors containing solid 6% by weight by weight. A liquor contains solids. What is the weight ratio? W by W is 6%. Now, due to evaporation by application of heat energy through steam or electricity, it evaporates. The output contains 30% solids in weight by weight. So W by W in the output is 30%. Calculate the evaporation of water for 100 kg of feed to evaporator. What is given? The input feed is given, that is 100 kg. So basis is input is 100 kg. What is input solid content? 6%. Output solid content 30%. Feed is 100 kg. So how much solid is there in input feed? 100 into 6%. So 6 kg. Now this 6 kg will remain same. Mass in is equal to mass out. So solid in is equal to solid out. So output solid will be 6 kg. But what is here given? The output solid ratio is W by W is 30%. So 30% is equal to 6 kg. So 100% will be how much? 6 by 30%. It becomes 20 kg. So output is 20 kg. But what is the input feed? 100 kg. So how much of water has been evaporated? 100 kg minus 20 kg. So 80 kg of water has been evaporated in this process. Now let us do an example on air composition. Air contains 77% by weight of nitrogen and 23% by weight in oxygen. Remember, the volume ratio is something different. 21 vis-a-vis 79. But weight ratio is 77 vis-a-vis 23. Now we have to find out mean molecular weight of air, mole fraction of oxygen, the concentration of oxygen in mole by meter cube, kg by meter cube. The total pressure is 1.5 atmosphere and temperature is 25 degrees centigrade. These are two important different parameters here. First, what we have to do? We have to first take a basis. Let us take a basis of 100 kg of air. Now, what is the molecular weight of nitrogen? 28. N is 15, 14. So N2 is 28. What is molecular weight of oxygen? 16 into 2. O2 is 32. So if 100 kg of air, it will contain 77, because weight is 77 by 28 moles of N2. 23 by 32 moles of O2. That means if I divide it, the moles of N2 will be 2.75, moles of oxygen will be 0.72. So total moles will be 3.47. So mean molecular weight of air will be how much? Moles is 3.47. It is present in 100 kg of air. So mean molecular weight of air will be 100 by 3.47. This becomes 28.8 kg. This is the mean molecular weight. This is the first question. Now mole fraction of oxygen is what? Molecular or number of moles of oxygen. What is that? 0.72 divided by total molecular or total mole of all constituent. That means 2.75 nitrogen and 0.72. It becomes 21%. So mole fraction of oxygen is 21%. Now, let us come to this problem. For this problem, we have to remember the gas equation. What it says? Pb is equal to nRT. What is P here? P is pressure. V is volume. N is number of moles. R is gas constant, which is 0.08206 meter cube atmosphere per mole degree Kelvin. We have to remember this number 0.08206 meter cube atmospheric by mole Kelvin. Temperature is 25 degrees centigrade. We need to convert degree centigrade into Kelvin by adding 273. So it becomes 298 Kelvin because gas law is applicable for Kelvin. Here T should be in Kelvin. Now, what is volume here? Basically, it is has asked the concentration in mole per meter cube. So let us consider a volume of 1 meter cube. Now you just apply all this in the gas equation. P is given 1.5, V is 1, N we need to know, and gas constant has been given or can be remembered. 290 is the temperature. So N becomes 0.061 moles per meter cube. Now, what is the weight of air in that case? This is the mole per meter cube. This is the molar concentration. So weight of air will be N into mean molecular weight. That will be 0.061 into 28.8. From where we got? Because mean molecular weight of air is 28.8 kg. So it becomes weight of air becomes 1.76 per meter cube. That is the weight of air. Now, if this is 20% is oxygen, so weight of oxygen will be in 1 meter cube of air will be 0.23 into 1.76, that is 0.4 kg in 1 meter cube of air. So concentration of oxygen is 0.4 kg per meter cube, and if I need to find out in moles, I have to divide it by the molecular weight. Molecular weight is 32. So 0.4 by 32 is becomes 0.013 mole per meter cube. So these are basically simple formula, but we have to remember this gas equation, gas constant, molecular weight of oxygen, and these are the simple conversions. That means here basis is in kg and the concentration of oxygen is 0.4 kg per meter cube. This is one, and when you find out mole per meter cube, you have to divide it by the molecular weight. With these simple assumption or theories, we can solve these problems. Now let us do another gas composition problem. In a carbonation of soft drink, the total quantity of carbon dioxide required is equivalent to 3 times volume of gas to 1 volume of water at 0 degree centigrade and atmospheric pressure. Calculate the mass fractions, mole fraction of CO2 in the drink, ignoring all components other than CO2 and water. That means in a cold drinks, it is a basically carbonized drink, carbonized water. That means water is there and you compress CO2 into it and we get soft drinks. But some kind of flavor, sugar are there. Here we are ignoring those components. First, what we have to do? We have to find out a basis. Let us basis is 1 meter cube water. That means it is around 1000 kg. 1 meter cube of water, density is 1. Now volume of carbon dioxide added will be 3 times, so 3 meter cube. Now we have known the gas equation, PV is equal to nRT. So 1 is atmospheric pressure, so P pressure is 1. 3 times, because gas is only applicable to the CO2. So gas equation is applicable to CO2. So volume of CO2 is 3. Now 3. N we need to find out. Gas constant is 0.08206 and 0 degree centigrade is basically 273 Kelvin. So from this I got N is 0.134 mole. Now what is the molecular weight of carbon dioxide? CO2, C is 12, O2 is 16. So 32 plus 12 becomes 44. So weight of carbon dioxide added will be how much? 0.134 mole divided into 44, because this is the molecular weight. So it becomes 5.9 kg of carbon dioxide is added here. Now we need to find out what mass fraction. So what is the mass of carbon dioxide added? 5.9 kg. What is the mass of water? 1000 kg. So mass fraction will be mass of carbon dioxide divided by total solution, that is 1000 plus 5.9. So this is the mass fraction. What is the mole fraction? Here the molecular weight, mole of CO2 becomes 0.134. Molecular weight of the water is 1000 kg. What is the molecular weight? 60. H2O is H is 1, O is 16, so it becomes 18. So this molar concentration will be 1000 by 18, and 0.134 is carbon dioxide moles. So mole fraction becomes mole of CO2 divided by mole of water plus mole of CO2. We are ignoring all other components. Then this value becomes mole fraction of carbon dioxide in the drink. Now let us solve another example of dust balance. A bag filter. This is basically a bag filter. Normally it is used to remove dust, to reduce the dust loading in the exit or flue gas, because if more SPM, solid particulate matters, goes outside the chimney, it will pollute the environment. So bag filter is basically to clean the gas so that it will collect the ash and clean gases goes to the atmosphere. A bag filter is usually used in cement, fertilizer, other chemical industries. Its basic purpose is to remove dust from the inlet gas stream to meet the emission standard of State Pollution Control Board as per CPCB guideline. Now, inlet to the in this problem, the inlet to the bag filter is 169920 meter cube per hour. This is the flow rate, and dust loading is here 4577 milligram per nm cube. So this much of dust is there. Now output gas outlet is 185040 meter cube per hour. This is the output flow rate. Now in this case, what is the dust loading? 57 milligram per nm cube. Now this fabric filter remove this dust so that clean dust or clean air is goes out. Now this dust accumulated so is collected as in forms of ash. So we have to find out what is ash percentage. Now for dust balance, mass in is equal to mass out. That means inlet gas dot is equal to outlet gas dot plus hopper ash. Now inlet dust quantity will be how much? This nm meter cube per hour into dust loading. Now this is milligram. This is basically mm cube. So what I have done, 1 kilogram is equal to 10 to the power 6 milligram. We have divided by 10 to the power 6 to have a simpler unit in kg. So inlet dust quantity is equal to 777.7 kg per hour. Outlet dust quantity will be how much? Flow rate into dust loading divided by 10 to the 6. It becomes 10.6 kg per hour. So what? How much of dust going? This 777.7 kg. How much of dust is coming out? 10.6. So what is as? This minus this becomes this as. So as becomes 767.1 kg per hour. So today we have read about mass balance. We have solved some numericals. Now let us study about energy balance. Particularly, energy balance means energy is the capacity to do work or to transfer heat. The law of conservation of energy states that energy can neither be created nor destroyed. The total energy in the material entering the processing plant plus energy added in the plant must be equal to the total energy leaving the plant. Basically, energy balance is based on law of conservation of energy. You all know energy cannot be created or not destroyed, but it is getting converted from one place to another or one from to another. Now we have to conserve useful energy. Energy balance is more complex because energy can take various forms such as kinetic energy, potential energy, heat energy, chemical energy, electrical energy during conversion. So it is very difficult to do energy balancing. Now in a system if the storage does not change, the ingoing and outgoing energy must be equal. In case stored energy decreases, then it may either go with product or get lost in surroundings. Now sinks are deposited of leakage or rejected energy. It is usually low grade heat as radiation losses from boiler or heat carried out by cooling water. The output depends useful work. Basically, these are the basic concept of energy balance, which tells that energy in is equal to energy out. Energy balance is more complex. Now, storage of energy. Let us see. Incoming energy is 75. There is no energy stored inside. No heat energy, nothing is stored. So out product is 15. The energy that has gone with the product is 15. And this 60 is waste. So this is basically a leakage or rejected energy. This is a low grade heat. Radiation losses of boiler, it can be anything. Or it can be heat carried out by the cooling water. And this is basically going as loss. Here there is no storage of energy. But in this case, assume that there is some stored energy is there. This because of process, all the energy could not go outside along the product nor with the loss. So stored there is an increase in the stored energy. So here, if what 75 will be the stored energy plus 15 plus 45. Now storage has decreased. Let us see some energy content which was earlier there, it has decreased. So it becomes product energy becomes 25, sink is 65, input is 75. There is a decrease of energy of 15. So basically these are all are sinks, which is basically takes care of or denotes the leakage or rejected energy. Then the product is basically the useful work in which the energy goes. And if the storage does not change, the incoming and outgoing must be equal. But if there is a storage either increase or decrease, in that case, the outgoing and incoming will not be equal. Now, let us let us do an example. Pasteurization process of milk. In pasteurization process milk, normally what happens? We get raw milk. There is a chiller to chill it. Normally it is kept in a chiller so to protect the milk. Then there is a tank. All the chilled milk is collected in the tank. Then during the process, first we have to do what? This is a 4 degree centigrade chilled milk. We have to heat it through either process of electrical heater or a boiler plate heat exchanger or through steam energy. So the steam milk is heated. After that, once it is heated up to the up to lower than its boiling point. Then what it is heated up to 72 degrees centigrade. Then again it is cooled by flowing cooling water. Then the temperature reduces and again it is chilled with the help of chiller, and then it is packaged and sold to the consumer. So this is the pasteurization process of milk. In this case, the milk is formed to the heat exchanger, first heated, then cooled. Now heat energy is added to the milk. There is a pump, there is a hot water. So here we are adding heat. Then cooling water removes the heat. This is basically it is removing the heat, and some of the energy is also lost to surroundings. Now in this case, if I do energy balancing, what I'll do, I'll see that heat energy leaving the milk is equal to initial heat energy of the milk, heat energy added by the pump because there is a pump, heat energy added in the heating section, minus heat energy taken out in the cooling section, minus heat energy lost to the surroundings. So this is the energy balancing during the process of pasteurization of milk. So we have to know that heat entering should be equal to heat outgoing. Now, but when you apply this energy or heat, what happens? There is an internal change in energy in the product or working fluid. So that is known as dW, or change in intrinsic or internal energy of the working fluid or in the internal systems. Now see the energy balance in a power plant cycle. What you exactly do? Q in, this is the coal energy, input heat energy. You give it to boiler. Now this is the boiler feed pump. This is the steam cycle. Water. This one is the steam energy. You apply heat, get steam energy. It goes to the turbine, rotates it. You get work out. That is the generator output or the turbine output, so that you can get some electrical energy. Now the steam boundary is this much. Then it is the steam energy is condensed, and with the help of condenser, this condenser is cooled by cooling water. Again, this raw water or the dam water is pumped through the help of boiler feed pump, and this process is repeated. Now, in this process, if you apply law of conservation energy, if a system undergoes a process by heat and work transfer, there is a process of heat and work transfer both. Then the net heat supplied, Q plus net work output, W is equal to change in intrinsic or internal energy, dW of the working fluid. That means dQ, all Q plus all work should be equal to del U. Now, applying general principle to a thermodynamic cycle, when the steam undergoes a complete cycle, change in internal energy del delta W becomes 0. So delta U is 0. Why? There is a no change in the process in a complete cycle. So water is starting, again it is coming back to water. So delta U becomes 0. So del summation of Q is equal to summation of work done is equal to 0. So del summation of Q becomes algebraic sum of heat supplied or ejected from the system. Summation of W becomes algebraic sum of work done by surrounding on the system or by the system on surroundings. Now with this, if I come to these problems, what will happen? Del Q is equal to Q in thermal energy, coal energy going into the system minus thermal energy going out of the systems. W in minus W out. That is the feed pump doing some work, and the turbine is giving output energy. So this pump is giving some input work, and turbine is removing output work. So Q in plus W in minus Q out minus W out. So this is the equations basically. Now let us solve these problems. The thermodynamic efficiency of a process is the ratio of useful output to input is always less than 100%. In the energy balance shown in figure 5.7, there is no internal storage. So the sum of input must be equal to outgoing energy. Efficiency of the process is 22.5%. Energy lost to the system is 77.5%. Efficiency of the process is 22.5%. Energy loss becomes 77.5%. Now this is the problem. Now we have to find out the solutions. Now see here, what is the input energy? 185, and this again 15 is the output or input work done. 155 is the output heat energy. 45 is the output work done. So input becomes 185 plus 15. Output plus sink becomes, output is 45, sink is 155. So from these we can find out what is the output. Efficiency will be, output is 45. What is the input? 15 plus 185, that gives 22.5%. So with the help of energy balance, we can find out the efficiency of the systems. We are worried for this output useful energy, and this can be improved or increased by reducing this heat loss. With this, I close this session. So I request you all to study the numericals, carry out the problems, solve those problems, and this is very important session as far as mass balance and energy balance is concerned. And in the next class, we'll conclude this mass and energy balance. With this, I stop here. Good night.